Okay. Good evening, everyone. Welcome to the final project presentation of the Equinox 2022 General Relativity Cohort. So today we have the General Relativity Cohort presenting about their final presentation on the anisotropic matter distribution on neutron stars. So can we begin, Aditya?
Yes, so we will be beginning. Five of us have co-authored this paper, and hence Sukhjit will be starting and Mainak will be presenting.
Yeah, please let me know whether the screen is visible or not. Is the screen visible?
Yes, Mainak.
Okay.
So can we begin, Sukhjit?
Sure.
Yeah, sure, let's begin. So please let us know that when you would like to begin, or should I start right now?
You can start right now. Yeah.
So hello everyone, my name is Sukhjit. So today we will be presenting our final project discussion on the anisotropic matter distribution within the neutron stars. So Manik, can you please go ahead? Okay. So here we'll be discussing the flow of discussion. So we will be starting with an introduction to the topic. We will start with a quick introduction to the basic terms and what is the need for new anisotropic solutions, followed by a quick discussion into the Einstein's theory of relativity. Our work and analysis of this project basically comprises of deriving the Einstein field equations and then using those equations to arrive at the algorithm. After that, we apply the algorithm and on some case studies and analyze the solutions in various scenarios. Then we carry out with the conclusion of the research study based on our analysis of the whole image sets and calculations. After that, we go to the discussion section where we have comprised our all research studies. Okay, so this is the abstract. So through this model, we aim to use the algorithm which has been developed by the S.G. Maharaj and M. Chessy to model the anisotropic neutron stars based on the fundamentals that have been developed through the Einstein's theory of relativity. We use field equations of the relativity to design a particular system of equation that helps explain how the matter behaves in all inertial frames of reference. To illustrate the formation of the stellar structure and detect the behavioral aspects, we found out that the frame of reference does not play any essential role, and it is only a mathematical structure that can be chosen as per the requirement of the person. So we also observe that, and we also analyze that due to the high densities of the matter within the neutron star, if we consider the case of an ideal star, which may be an ideal choice, but it is very far from the most practical one. However, through our discussions, we found out that understanding how the conditions are in an ideal cases, we may be able to further strengthen our knowledge of the practical cases. So through inclusion of the anisotropy in the isotropic calculations, we found out that these conditions can further be derived and solved. So following our analysis of the results and comparison of the results, and we found out that the interaction of the stellar structure forming within the local system can be understood, and theoretical considerations and results can be further evaluated. Yeah. Okay. So now we will give a quick introduction to the neutron stars, isotropy and anisotropy, and relativity. So what are neutron stars? So it is basically defined as a dense celestial object which comprises of closely packed neutrons together, which results from the collapse of a much larger stellar body. So they are they're typically about 20 kilometers in diameter. So that's smaller than the size of Texas itself, and their masses mostly range between 1.18 to 1.97. But surveys from Hubble Space Telescope to various ground-based telescopic surveys, they found out that these are most likely in the range of 1.35 times the mass of the sun. Now, the gravity of a neutron star is actually 1,000 billion times stronger than that of the Earth, despite its smaller size. Isotropy. So isotropy is basically defined as a property which exhibits same properties with the same values when measured along in all directions. This is one of the assumptions that have been taken in the theory of relativity also. However, anisotropy is completely opposite of anisotropy in the case that it exhibits properties with different values when measured along axes in all directions. So in our project, anisotropy typically refers to the variation in matter distribution within a neutron star. That is, we say that the density is not radially symmetrical, and this leads to a further plethora of phenomena concerning the set star. Based on this assumption, we can discuss about a number of cases. A number of research problems can further be derived from the case of anisotropy itself. Relativity. So relativity includes two theories which were proposed by the Albert Einstein in the year of 1905 and 1915 itself, which have been called as special theory and general theory of relativity. Where special theory of relativity is an mathematical explanation of how speed affects mass, time, and space, general relativity is in itself a geometric study where it shows that how the matter wraps the space-time, and how space-time's curvature dictates the motion of masses in a number of conditions. So why do we need anisotropic solutions? Modeling of stars. So earlier studies that were done before the relativity, we assumed there that the matter content within a star is a perfect fluid, which can be characterized by an isotropic pressure. However, we found out that it was difficult to create more models as we had very less knowledge of the internal structure of a star, in particular how the gases have been distributed. It was only under our basic assumptions that we were assuming them. And it was more difficult to find out the behavior of the gases, especially at the boundary conditions. So later works consider the possibility of the existence of anisotropy within these stars. So the understanding of this study that how a given stellar body, which is in a hydrostatic equilibrium, can consist of a perfect fluid would also be desirable. So this would further help in understanding and strengthening our knowledge of the implications of the situation when the conditions are not isotropic. Okay, I will be giving up to Devaditi now. He will be carrying on from here. Devaditi, are you there?
Yeah, thanks, Sujit. So now we, in our paper, we heavily rely on the theories of relativity. So we need to brush up a little on our theories, on the theory of relativity understanding. So the first that comes is the special theory of relativity, which gives the basic, without any gravity, and the understanding of space-time without any gravity. And then comes the incorporation of gravity into it, and it is general theory of relativity. Then we will see how we model the neutron stars, that is our project, using GR. So now, firstly, we knew from Galileo that there's the possible practical situation where we need two frames of references, and it like the situation where we are in a platform and someone is in a train, the two frames of references are different from the perspective of the train, an observer in a train and the observer in a platform. The Galilean transformation was known previously, but then came the Lorentz transformation for 2 frames, which were moving with a relative velocity v, and these equations dictate how the space-time is changed from one frame of reference to another frame. The gamma here represents the respective velocity with c, that is the speed of light. So the next slide, please. Yeah. Now we need some mathematical notations and formulations to understand this general theory of relativity and special theory of relativity as well. That is a tensor, and tensors are really a mathematical quantity or representation that represents a physical quantity, but these are of two types, the covariant and the contravariant tensors. The covariant tensors in notation form are denoted by the lower indices, that is A0, A1, A2, A3, which have the lower indices at the bottom. And then we have the contravariant tensors, which have the A0 minus A1, which is equivalent to a covariant tensor A1 in the low with the lower indices. So the contravariant tensors looks like with the upper indices. And then we have a Minkowski metric, which is the measure of the distance and defines the structure of space-time that we are concerned with. It connects the covariant and the contravariant tensors, which is given in the last equation of the slide, how it connects a covariant and contravariant tensor. And this Minkowski metric actually describes a flat space-time. So the relativistic concepts, these flat space-time Minkowski concepts, these are very well represented as space-time diagrams. And in the diagrammatic form, we use the z-axis, that is the vertical axis, as the time axis. And we suppress from 3 space axes, we suppress 2 axes, and then we use a single space axis, say the x-axis, and we represent it in a 2D fashion so that we can represent it on a flat surface like the monitor of whatever device you are using. This represents the whole of space-time, and the observer is supposed to be at the center. Now a photon travels at the speed of light. So the photon traveling at any direction makes a 45-degree line with the space and the time axis, which means it just travels equally among the space axis and the time axis. And any practical object just travels slower than a speed of light. That means it falls under the cones, which are the past light cone and the future light cones. These cones represent the future and the past incidences which can impact the observer. The observer can interact with the past light cone, that is past events can affect him, and the observer can affect any incident or event that is in the future light cone of his or her present situation. Okay, then we now move on to general theory of relativity, and Einstein's general theory of relativity describes the nature of gravitation and provides a connection of what we perceive as gravitation, and is a generalization of the special relativity as it incorporates gravity, which was not incorporated in special theory of relativity. The gravity is incorporated here as a measure of the geometric structure of space-time. Then to understand that, we must get that we have a space-time fabric, manifold, if you can say. On that, any object is like in a free fall between two points, and it always takes the shortest path possible. So between any 2 points, the shortest curve in any arbitrary surface is represented by an equation, which is the geodesic equation. And here the tensor notations might be too hard to understand, but I'll give you the physical understanding of it only. Not going into too much mathematical details overall, because that needs many more discussions and time. So the Christoffel symbols used there represents a very important connection between the change in the vectors of a particular coordinate system. And these are exactly tensor quantities, although it has upper and lower indices like tensors do, but this is not typically a tensor and it only represents a connection. So then we have parallel transport. The concept of parallel transport is important as it refers to the shifting of vectors. Like we generally know that vectors can be parallelly shifted when we perform any basic vector mathematics. We can parallelly shift the vectors in our flat plane or flat surface, what we are considering in that problem. But in curved space, the shifting of vectors changes its direction, and the curved space is not like a flat space that can preserve the vector as it is when it is parallelly transported. So here the parallel transport concept means that we are keeping the vector somehow constant and then we are shifting the vectors on that manifold itself. And this parallelly transported path, while preserving the vector or the tensorial nature, that is vectors are only a sub form of tensor. I mean, tensors are the generalization of vectors in higher ranks. So preserving the tensor, if we transport parallelly the path we are considering, then the instantaneous rate of change, as we do in a case of flat space, the derivative here in this case is called covariant derivative, which preserves the vector. So next slide, please. Yeah, then with all these curved space terminologies and all, we only aim to achieve that we measure the curvature of a certain space-time, that is with a body which has a gravitational field and which curves the space-time around it. So to measure the curvature, we need some particular quantities, and these are the curvature tensors. First of all, there is Riemann tensor, which measures the curvature of any nth dimensional space-time, and we can contract it. That is, we can multiply kind of with the metric tensor, and we can contract it to form the Ricci tensor. The Ricci tensor only has two indices, but it contains the necessary information of the curvature within it. And then we have, on further contraction, the Ricci scalar. While the Ricci tensor, please go to the previous slide. Yeah. While the Ricci tensor gives a measure of the change in volume of a certain shape, when it is transported along the geodesic, that is the shortest path as we discussed, it is deformed in a way which is measured by the Ricci tensor. And the Ricci scalar characterizes the intrinsic curvature, the curvature which is inbuilt in the space-time and not because of some coordinate. This will come later on, that we can see some point where there is a apparent curvature from the space-time coordinate system that we are using. But the Ricci scalar just measures the curvature which is intrinsic to the space-time and not give us any apparent measures. So it is a true measure of the curvature. Okay, next slide, please. Now we arrive at the most important equation, that is the Einstein field equations. To derive it, we used the Einstein-Hilbert action, that is SEH represented here, and which is kind of obtained intuitively little bit, but then we can use it to according to our observations and according to our known principles to tweak it and then get the final form of it, and the variational formulation which gives the actual equation of the particle of any particle which is on a space time that is we are concerned with, and that dynamic of the space time is represented by the Einstein field equations, which are the box equations. These contain many equations in one short equation because the tensors actually are dependent upon the indices, and the indices here represent many equations. So the R mu nu, as we know, those are the Ricci tensors, and R is the Ricci scalar, and lambda here is the cosmological constant, which was introduced to describe a curved, describe a evolving universe that is expanding. Einstein introduced it, and then the T mu nu, which is the stress energy tensor, and we have the stress energy tensor defined as a way of arriving at this equation via the variational formulation. Okay, the next slide, please. Yeah, then Karl Schwarzschild solved the Einstein field equations to describe the gravitational field outside a spherical mass under the assumption that space is a vacuum. That is, he solved assuming that there is no gravitational matter. So we have T mu nu that represents the stress energy tensor, that is the energy that is the gravitational body's stress energy tensor, which represents the matter content in the space time, that is 0. There is no gravitating body. So we have this metric dA square equals 1 minus Rs by R and so on. This metric is the solution of the Schwarzschild exterior solution, that is outside a spherical mass, and Rs represents the Schwarzschild radius. The Schwarzschild radius is important in a sense that there is a significance of it in the form that it forms the event horizon of a black hole. I mean, it's not relevant really, but it gives the measure where the event horizon of the black hole occurs for a mass m, I mean gravitating body with mass m. Then we have the metric for the interior solution, which is equivalent to the exterior solution, but it represents the gravitational field in the interior of a spherical symmetric body, and this spherical symmetric body may be is assumed ideal case, but it has a continuous transformation from the interior solution to the exterior solution. As we can see that if we substitute the R in the interior solution with R naught, then we get the exterior solution, as the metric of the exterior solution represents the field of the gravitating body outside the mass m body, but the interior solution is the same thing, which represents the inside of the body. Then we set it, if we set the R as the radius of the body, then it goes into a continuous transformation from the inside to the outside. Okay, so yeah, then for the next part, I will hand it over to Aditya.
Thank you, Debadyuti. I'm just making sure I'm audible.
Yeah.
Awesome. So now, since Debadyuti has given all of us a background of what general theory of relativity actually contains and what kind of mathematics we are going to be using in doing what kind of mathematics we have actually used in the duration of this in this project. I won't exactly go into all those rigid and rigorous mathematics, but I just want to illustrate how we actually did this project in a short algorithm, and just paint everyone present here an idea of what this project actually contained. Next slide, please, Mainak. So we had an isotropic metric, a line element for a spherically symmetric space-time, a bit similar to what the Schwarzschild sphere was already given. That was an assumption. Plus, we had a metric with isotropic assumptions. Please remember that our aim was to generate an algorithm to model anisotropic neutron stars, but we begin with isotropic assumptions and we calculate Christoffel symbols, Ricci tensor and Ricci scalar. Like Deepadyuti had previously mentioned, we have the various formulas that I will be showing in the project report after this presentation. For now, in the algorithm, the process that we follow would be the getting the metric with isotropic assumptions. Using that, we calculate the various components of the metric. We calculate Christoffel symbols that help us in calculating Ricci tensor and Ricci scalar. And with a given stress energy momentum tensor for the radially symmetric mass distribution of fluid within the neutron stars, we get to solve it for the Einstein field equation. Our modeling was Einstein field equation, and since the star is there spherically symmetric and static, the cosmological constant was assumed as 0. As Debadyuti mentioned, the cosmological constant or lambda was there as a constant, as a correction for an evolving universe, for the expansion of universe that we talk about. Hence here we take terms that are void of lambda, and then we add a certain measure of anisotropy in this, and with that we compare the anisotropic solutions to the isotropic solutions to calculate the measure of anisotropy and also to model the stars and to analyze the various examples that Mainak would be showing now. Over to you, Mainak. Thank you.
Okay, so am I audible?
Yes, Mainak.
Okay, great. So thanks, Aditya. So now we will explore a few examples and we'll try to apply our previously mentioned algorithm in these specific cases. Also, then we will discuss the observations relating to those examples. For our first example, we considered the isothermal spheres. Now, isothermal sphere is a configuration of infinite radius converging asymptotically to 0 and having infinite mass. The line element of such a sphere is given by this following expression. The first expression that you can see on this slide is the line element of such an isothermal sphere. Now, when we apply our previously mentioned algorithm on this line element, the anisotropic effects also come into consideration. And the new line element for the anisotropic isothermal sphere thus becomes like this, the second expression that you can see. Now, comparing these two expressions and using certain mathematical methods, we obtain the degree of anisotropy as the third expression given by S equals to K by 2 square root of 3 into R to the power of coefficient. Okay. So now we see that this expression of degree of anisotropy contains two parameters, namely K and C, varying whom we get different plots of S versus R. So I will now be showing you the plots in the next slide. So Here we can see that these are the 2D and 3D plots of S versus R for changing values of K, keeping C as a constant. We observe that initially, when K is 0, as we can see in the 3D plot, when K is 0, the S, that is the degree of the anisotropy, is also 0, and it doesn't change with R for K equals to 0. But as K continues increasing and changing, the slope of SR also increases gradually with changing R. You can see it in the 3D graph and the 2D plot as well. So moving on to the next slide. Here we observe a peculiar characteristics of the graph. This is basically the graph of SR versus R for changing values of C, keeping K as a constant. We see here that when C is in the positive region, the whole graph is of decreasing nature with respect to R. But after C enters the negative domain, here as you can see in the 3D plot, it's more obvious. When C is entering the negative domain, for a small region of C, the whole graph changes its nature and SR starts increasing with R. You can see it here. The graph is increasing with R. But then as soon as C crosses this region, the small region, the graphs again bounce back to the same characteristic as initially in the positive domain. And don't worry, these things will be demonstrated in a live section as well, just after a few slides. So now we move on to our second example. As we can see in the slide, we are considering the interior Schwarzschild model here and are applying the algorithm to the Schwarzschild sphere to check its applicability in this case. So the line element of this model is given by the following equation that you can see on the screen, where delta is defined as square root over 1 minus small r squared by capital R squared, and R is analogous to the Schwarzschild radius of this sphere, considering the interior Schwarzschild solution as seen in the Schwarzschild solution part. Also, A and B are constants here. Now, again applying the algorithm on that previous line element, we get a new element for the anisotropic Schwarzschild sphere. This big equation that you can see is that line element of that anisotropic Schwarzschild sphere. Now, similar to example 1, we compare these two equations, one for the anisotropic sphere and that one for the isotropic sphere, and we come to get the degree of anisotropy, which is given by the second equation. Now here we see that this degree of anisotropy expression contains the term A, B, capital R and K, varying which we get different plots of S versus R. So these are the plots that we get for various K values. We are keeping the other parameters as constant over here. We see that similar to example 1, here also the plots are initially decreasing in nature and they are attaining saturation at higher values of R with increasing values of K. I mean, if you continue increasing K, as you can see in this 2D plot here, we get that the saturation of SR is happening at higher values of R. It can also be seen in the 3D plot. Also, similar to the previous example, as K tends to 0, our SR also tends to 0. Next, this is the plot for varying values of capital R, that is the Schwarzschild radius mentioned previously. We see that as R changes, the anisotropic effects extend up to R, beyond which there is no existence of anisotropy. That's quite obvious, as R is the radius up to which the matter distribution exists, so there cannot be any anisotropy beyond it. So this ends our presentation demo. Now it's time for some live demonstration. So I would like to pause the presentation here and would like to open up a new presentation. Just a minute. Okay, is the screen visible?
Yes, Mainak, it is.
Okay. Okay, so till now all our demonstrations have been basically static. Now we are going to show you all the changing plots with respect to different parameters in real time. First of all, we are considering example 1. So as I said earlier, you can see it here. If I change the value of k, the S versus R plot remains of the same nature, that is the decreasing anisotropy with R, but the saturation is being attained for larger values of R with increasing value of K. You can see it here. Also, if K becomes 0, you can see the graph becomes of 0 value. That is, there is no anisotropy at 0 value for K. Now the main catch comes when we change the values of C. Let us keep the value of K at an arbitrary point. Now we see that when C is in the positive domain, it remains decreasing in nature, but it isn't changing its nature anyway such. But once we take C into the negative region, we see that it abruptly changes its nature. As you can see in this region, it suddenly becomes of increasing nature. That is, the anisotropic effect is now increasing with the values of R. This phenomena basically continues for a small range of C in the negative domain, beyond which, if we just go on decreasing C, you can see it bounces back to the decreasing nature, as we saw in the positive region of C. So let me show it to you once more. Initially, in the positive region, the graph was of decreasing nature, but as soon as it enters the negative region for a small region, it changes its type to increasing, and then it again becomes decreasing in nature. Okay, so now we exit this example 1 and we will go to example 2. Just wait. Okay, please confirm if you are able to see this window.
Yes, Mainak, the window, for
Okay,
example, is visible.
Yes. So now, as we saw previously, that in example 2 there are 4 parameters K, A, B and R. So basically here the K plays the same role as in example 1. You can see that is, it's changing the point of saturation for varying K, and if K becomes 0, the whole graph becomes 0. That is, there is no anisotropic effect as such. Now, as I mentioned previously, R is the Schwarzschild radius. So it restricts up to which value of R the anisotropic effects will be seen. As you can see, now R is changing, and the anisotropic effects up to which value of R it is being shown is also changing. If R is 3, the anisotropic effects are being shown up to 3. And this is the case for each and every R. So let's consider a certain value of R. Now, A and B, okay, no, sorry, B behaves in a same way as of K. So basically, when it decreases, the point of saturation also decreases, and when it increases, it also increases.
Which software are you using for this simulation?
Actually, I have done it on Python using Matplotlib.
Okay, so this is, I mean, you are just showing us the Python's output, right?
Yes, I'm just showing you the output screen.
Good.
So, and then if we just make B0, then we see that the whole plot blows up. There is basically nothing. A behaves just in the opposite way to that. If we decrease A, the point of saturation goes up, and if we increase A, the point of saturation goes back, becomes lesser and lesser. So these are the observations that we concluded from applying the algorithm on those two examples. And so that's all from my part. So next I will share the screen once again and will hand over the presentation back to Aditya. Just a second. Okay, over to you, Aditya.
Thank you, Mainak. So after all of these observations, after doing the mathematics, after initially learning the mathematics, then doing it, applying it to various examples, and then after taking the examples, we finally conclude. Next slide, please.
Mhm.
That general relativity, we finally understand how general relativity affects the space-time, how it makes matter, how matter makes the space-time curve, and how the curvature of the space-time tells matter how to move. The randomness or the anisotropy in the distribution of the fluid content within the star is evident because that is a fact in nature, and understanding it is more realistic. It's better than just trying to deal with isotropic cases, but it is also evident that without the existence of the isotropic assumptions, there it would have been presumably um, we would have presumably insufficient work to derive the anisotropic conditions. And using this and through this program and our work in this project, we understand the way general relativity can be used to model celestial objects. It can be used to understand the nature of space-time and matter distribution throughout space-time, and the way how celestial bodies such as stars behave and dictate the space-time around them. Mainak, here it's the five of us. There's me, Debadyuti, Mainak, Nihar, and Sukhjit. The five of us, under the able guidance of Dr. Dishant Pandya, and through this program of Equinox by Naxxatra, we were able to study the matter distribution within neutron stars and also to know about general relativity, special relativity, and the various advancements in the way scientists study to know more about the universe, and stepping stone for our future endeavors. It's evident that this project was only made possible all thanks to Naxxatra and under the guidance of Dr. Dishant Pandya, and thank you to Sagar and Vikrant for helping us know more about special relativity, general relativity, and the various mathematics, the rigorous mathematics that goes along with it. Also, before moving to any questions, I would like to share my screen. And Mainak, can you please give me the access? And I would like to
Yeah,
show
sure.
about. I would like to show everyone the report that we had worked on. Is my screen visible?
Yeah, it is.
Right from the very beginning, I would just I would just give an overview of what the report actually contains. It is not the gist, it is actually the entirety, the collection of everything that went on in our project, everything that we learned, studied, and understood through our report. So, if we just go to the later sections that I would be going on to eventually, we can understand the various plots. Apart from the live demonstration, we can understand what it actually means, the values of K, C, A, and B, why it occurs in such a manner, and why do negative values exist, and why, and in some cases, why do we only need to take the positive values. That's all due to the way the line element was, the way the algorithm was, and the algorithm that we have been talking about on for so much is in the coming few slides. This is what Debadyuti was talking about, the various mathematics that the various mathematics regarding general relativity that we had to first get acquainted with, and then to go on with the project. As of now, in your chat boxes, Mainak has shared the references. One was the paper on which we modeled our project on by S.D. Maharaj and M. Chaisi, and the one that we used as a reference was a conference paper by Dr. Dishant Pandya and Dr. Tikekar. The links to both of which can be found in the chat box in the Zoom meeting right now. And moving on with the report, starting with general theory of relativity. This is the field equation by Einstein, solving which we were able to do the said modeling of the neutron stars. The geodesics, what they actually mean, what is the parallel transport problem, and the important tensors that we were talking about are all talked about in better detail than the presentation inside the report. How the Einstein-Hilbert action that suddenly jumped up in the presentation is actually mentioned over here. Why is it needed? And how do we actually end up at this Einstein's field equation? It's not a single equation actually. It's a group of many differential equations which we solve accordingly to our given conditions. Carl Schwarzschild did it first for spherically symmetric static mass distributions, or what we call as is stars, since in the vast space, such fluid distributions are basically what stars actually are. This is how we use the field equation. We arrived at them, and how the algorithm actually works. And this section contains all the metric calculations, all the calculations that we had to go through, mentioned both as a reference, as an aid while reading the paper. It contains basically all the essential calculation that one occurs while reading or doing such kind of calculations in this paper. And onto the graphical analysis part, what Mainak just displayed, the explanations to the observations that were evident to us in this entire project are mentioned here as well. And onto the references. The references can also be found in the chat box that Mainak just gave. The two most important references, like I mentioned, the paper by uh, S.D. Maharaj and M. Chaisi, and the conference paper by Dr. Pandya. Back to our presentation part. Any questions, discussions, or feedback, please do tell us. Thank you all.
It was a very good presentation, Aditya and team. Dishant sir, would you like to give any feedback on the?
Yes, this was truly an excellent job you all people have done, and I must congratulate all of you. First of all, it was a very good teamwork, and secondly, I mean, it's really a difficult task when we are not together face to face, and still you have really done this all things nicely. Your I have gone through the full report made by you, and they also made few suggestions, and Vikram might have delivered to you so that you might have incorporated all those minute changes, right? Yes or no?
Yes, sir. First of
Okay.
all, thank you, sir. And yes, Vikrant had communicated all the
Yes.
changes, whether big or small, and we tried to incorporate it everywhere. So, yes, this is according to the corrections.
Yeah, good. And secondly, even within few pages, you have nicely presented the full thing. The person who has not came across such kind of real world problems, or you can say research problems, if they are just going through your report, then definitely he or she must get a good idea that how such kind of computations work, what is the role of general theory of relativity while dealing with the anisotropic matter distributions for such neutron stars and having exotic matter. So this is, I mean, truly good thing. And those who are interested, they may carry forward this work. One thing what I really liked here is many of the students, they are, if they are not having a good command over Mathematica, and still they are either of the ways they are using, like maybe from MATLAB or maybe through Python, they have generated the graphs which are interactive. So this was, I mean, truly commendable job that you have done at graduation level, that you incorporated these equations. And moreover, what the main thing which really touched to my heart is when you were explaining all these things, every detail you have covered. It was not a superficial presentation. You have covered each and everything. And one more thing is that you have shown the graph interactively. That was truly recommendable, I mean, commendable thing that you have done. So, I mean, as far as concerned to today's presentation, there is no suggestion from my side, but I'm congratulating all of you. And keep in touch. It's not like that we have finished this project and hence there is a full stop here. Okay, I'm always available. You can always approach me for your future work as well. Okay, we will have a good discussion and possibly the collaborative work as well. Wishing you all the best.
Thank you
Thank
so
you.
much, sir.
Okay.
Thank you, sir.
Thank you, Dishant sir, for your wonderful suggestions and valuable guidance throughout this project. So, is anyone from the audience have any questions? Vikrant, if you can you on your mic and give your feedback?
Hey, can you hear me?
Yes.
Yeah, so the thing is, I'm traveling in train right now, so I don't know how much of it can you make out. But then, yeah, I'm afraid I couldn't attend the entire presentation. But I've read the report. Dishant sir and I have gone through it several times, and we were really happy with the work that you've done. And I totally agree with the graphs that Dishant sir just said. You guys have done a really great job with both two-dimensional and three-dimensional graphs. And we talked about how you should explain all of that, and I'm pretty sure you've done that really well. I'll have a look at your report again. But again, congratulations on finally finishing the project, and I'm looking forward to you guys carrying it forward because you've invested so much of your time in it, and I'm pretty sure you're gonna get very good results if you carry it forward. All the best for that.
So much, Vikrant. It was a lot of your effort as well into what we have actually achieved today. So, uh, it's everyone's opinion that you are the person worthy of receiving the praise as well. Thank you so much.
Thank you. Thanks a lot. Thanks a lot. And of course, it goes without saying, thank you, Dishant, sir, for agreeing to guide these people for the project. And the discussions I've had with you were really fun.
It was my pleasure, but I mean, really, as Aditya said, your efforts are really 90%. I mean, whatever you have carried, otherwise, I mean, without your efforts and the explanation by Sagar for special relativity and general theory by you, it was, I mean, definitely not possible for the students in this way that they can carry out this much beautiful task. So heads off to efforts by both of you, Sagar and Vikrant.
Thank you very much, sir. So I don't see any questions in the chat box. It's fine. So what I'll do is I'll give you all the link of Naxxatra discussions. If you have any questions after going through the report, you can always join the group Naxxatra discussions, and then you can ask your questions. Vikrant and I will be available to answer. Yeah, the link is in the chat box. And that's it, guys. Thank you very much for your very wonderful presentation. And I'll also share the live stream, the recorded video link, the YouTube link in the chat box and in the Naxxatra live discussions. Okay. Thank you, everyone. Bye.
Thank
Bye.
you all.
Yeah.
Thanks all.